Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the energy separations in joules, kilojoule per mole, and EV electron volt between the levels n is equal to 6 and n is equal to 5 of an electron in a box of length 1.0 nanometers. So the first thing you have to do whenever you have a question like this is for you to read it to pick out the keywords. So we're told to calculate the energy separations in joules, kilojoule per mole, and EV. So we're going to have to do three different um, solutions, like solving for the energy separation in three different units in joules, kilojoule per mole, as well as electron volts. Between the levels, n is equal to 6. N is just basically quantum number. And we have between the levels, n is equal to 6 and n is equal to 5. Of course, since we're doing energy separations, we're trying to see the difference in energy level. So it has to be between two quantum numbers. So n is equal to 6 and n is equal to 5. So that's the short range of an electron in a box of length L. So they've told us that there is a box available here, and yeah, and in a box of length L. So the first thing you have to do is to first of all write out the parameters that you're given. We're given joules. We're supposed to solve for this in joules, in kilojoule per mole. Okay. So we need to find that one as well, the energy separation in kilojoule per mole. And then lastly, we need to find it in EV. So what is the answer in EV? So yeah, that's basically it. Before we go on to solve it, I want to quickly mention that this question is from the Atkins Physical Chemistry 11th edition textbook. And in the textbook, we know that there is a formula to solve questions like this. And the formula is just simply E sub n plus 1, okay, minus E sub n is equal to 2n plus 1, close bracket, h squared divided by 8ml squared. So this solution or this formula is from the Atkins Physical Chemistry 11th edition, and is the formula that you use to solve the energy separations between two different energy levels. So in this case, we have n is equal to 6 and n is equal to 5. So what they're asking us in essence is to find the energy level between E6 minus E5 in joules, in kilojoule per mole, as well as in electron volts. So that is basically what we're supposed to solve for. Now we look at our formula and see what we're given. We see that we're told we're going to need n to substitute. Well, E sub n plus 1 and E sub n. N is going to be the lower quantum number, and in this case, the lower quantum number is 5. So we have n is equal to 5. Another way you can look at this is just to match these two information here, or you can say n plus 1 is equal to 6, hence n is equal to 6. So anyways, n is equal to 5. The next thing we have is that we're given h. What is h? Well, h is just simply the Planck's constant, which is just a constant value all the time. I'm sure if you've been watching my videos on physical chemistry, you're going to already know what a Planck's constant is. Because if you don't know it, try to memorize it. H is just simply 6.626 times 10 raised to the power of negative 34 joules seconds. So that's that. And then, of course, we're given m. What is m? M is just simply the mass of the electron. Don't forget, we're dealing with a question that tells us the energy separation between levels of an electron. So m being mass, we have to use the mass of the electron. And the mass of the electron, if you've done physical chemistry, it is something that you're supposed to like pay attention to. The mass of electron is just simply 9.109 times 10 raised to the power of negative 31 kilograms. So this is basically what the mass of an electron is. Very, very tiny. And then, of course, L is just simply length, and which is just simply the length of the container. And the container is of length 1.0 nanometers. So 1.0. So the length of the box is just simply 1.0 nanometers, or I can just simply say 1.0 times 10 raised to the power of negative 9 meters. So we have the number of moles, we have the value for H, we have the value for M, and the value for L, and we can just simply substitute. So yeah, that's it. That's basically it. So E sub 6 minus E sub 5 is equal to 2n plus 1. That's just simply 2 times 5 plus 1, okay, multiplied by h squared, which is just simply 6.626 times 10 raised to the power of negative 34, okay, joules seconds all squared, because we're substituting the value for H. So we have successfully substituted the information in the numerator, okay. So this one divided by what is in the denominator. So you have 8, which is the first one here, times the mass, which is just simply 9.1094, or sorry, 9.109 times 10 raised to the power of negative 31 kilograms, okay, multiplied by the value for L, which is just simply 1.0 times 10 raised to the power of negative 9 meters, and of course squared. Let's not forget the squared. Now you're going to be wondering, okay, we've successfully solved. Now you're going to be wondering, okay, we've successfully substituted this information. So let us just square what we need to square and work it all out. Don't forget that we're told to get our final answer in joules. And this is one thing with physical chemistry. Every time you're working, you have to keep on looking at the units. Our final answer is supposed to be in joules. Don't forget energy separation, E6 minus E5. They told us to find in joules, kilojoule per mole, as well as in EV. Now, energy generally, the unit for it is joules, but we have a situation here. If we multiply joules seconds and we squared it, what we end up with is joules squared, seconds squared. And then at the bottom, we're going to have meter squared. And then at the other bottom, we're just going to have kilograms. Our units are all out of order. And we want our final answer to simply be in joules. Yet we have a bunch of different units that when we square it or do anything with it, is just going to make it much more complicated. So the best thing you do in a situation like this, E sub 6 minus E sub 5, is very, very, very simple. You just have to remember that when you're given multiple units, we have to break down all the units to the proper base SI units. Joules is simply kilogram meters squared per second squared. So this is the base SI unit for joules. And the reason is because the unit for energy is joules, and energy is just simply force times distance, where force is just mass times acceleration, and then there's distance. So really the formula for energy is just simply mass times acceleration times distance. And when you break down the units for that, you have the mass is just kilogram. The unit for mass is kilogram. The SI unit for mass is kilogram. The SI unit for acceleration is meter per second squared. And the SI unit for distance is just simply meters. So that's how we have kilogram meters squared per second squared. So this thing can also be seen as joules. You can rewrite it as joules. So I'm going to substitute kilogram meter squared per second square in every point in time that we have joules, so that our work is actually easier to work with and we're not left with a complicated mess. So yeah, that's it. So I'll rewrite E6 minus E5. So E6 minus E5 is the same thing as 2 times 5 plus 1, 2 times 5, close brackets, plus 1. Oof, would have messed up our work. Multiplied by 6.626 times 10 raised to the power of negative 34 joule seconds. So 6.626 times 10 raised to the power of negative 34, okay, kilogram meter square per second square. But let's not forget that we have the seconds right here. So we just say multiply by seconds, okay, and all of this information squared. Okay, so let me make the brackets here a little bit bigger to show that it's everything we're working on here. So yeah, that's it. Divided by 8.8 times 9.8 times 9.109 times 10 to the power of negative 31 is going to give you. So let's just basically multiply this one to make our work easier. So you have 8 times 9.109 times 10 to the power of negative 31 kilograms is going to give you 7.2872 times 10 to the power of negative 30, okay, kilogram, okay, and then 1.0 times 10 to the power of negative 9 meter squared. We can just square that. And when we square this information here, we end up getting 1.0 times 10 to the power of negative 18 meter squared. Okay, so that's it. E6 minus E5. So now let us basically do all our work and put the proper units. 2 times 5 is 10. 10 plus 1 is 11. So I've changed the marker. Next, 6.626 times 10 raised to the power of negative 34 squared will simply give you 4.39039 times 10 raised to the power of negative 67. So that's that. I'm now going to focus on this one right here. I'm going to focus on this unit. Don't forget that even though we have the joules to be kilogram meter square per second square, we're not really dealing with just joules. We're actually dealing with joule seconds, which is the unit for the Planck's constant. So we can just simply cancel out the seconds here since these ones are like terms, seconds. So what you end up with is kilogram meter squared per second. And then all of that information is squared because of the raised to the power of 2 that we have. So when we do that, kilogram squared is just simply kilogram squared. Meter squared squared is just simply meter raised to the power of 4. And then, of course, the denominator is just second. So second square is just second square. So s squared. So that's it. Divided by 7.28 times 10 raised to the power 7.2872 times 10 raised to the power of negative 30 kilograms times 1.0 times 10 raised to the power of negative 18 meters squared. So let me just rewrite that. So 7.2872 times 10 raised to the power of negative 30 kilograms multiplied by 1.0 times 10 raised to the power of negative 18 meter squared. So now this is a perfect time for us to cancel out all the units. So let's cancel out the kilograms in the denominator, cancel out one of the kilograms in the numerator, cancel out the meter square in the denominator and meter square from the numerator. So we end up with, rather than m raised to the power of 4, we end up with m raised to the power of 2. So that's m squared. So we have all this information. We've canceled out all the units. So e sub 6 minus e sub 5 would just simply be 11 times 4.39039 times 10 to the power of negative 67 is just going to give you 4.82943 times 10 to the power of negative 66. The unit that is left here is just simply kilogram. Then you've got meter square, and then you have per second squared. So you just end up with kilogram here, meter squared, per second squared. All of this information divided by 7.28 times 10 to the power of negative 30 multiplied by 1.0 times 10 raised to the power of negative 18 will just simply give you 7.2872 times 10 raised to the power of negative 48. Okay, so that's that. Yeah, that's basically it. So the next thing you have to do is just simply 4.829 times 10 raised to the power of negative 66 kilogram, meter squared per second squared divided by 7.2872 times 10 raised to the power of negative 48. When you do that, e sub 6 minus e sub 5 is going to end up giving you 6.62728, okay, times 10 raised to the power of negative 19. And then, of course, you've got kilogram meter squared per second squared. We know kilogram meter squared per second squared is the same thing as joules. So we're still going to get our final answer in joules because that's really what they asked us to do. So our work is just e sub 6 minus e sub 5 is going to equal 6.62728 times 10 raised to the power of negative 19 joules. Now, we are chemists. Our work is still not done. We have to put our work in the proper number of significant figures, and that requires us to go back to our question and pick the right number of sig figs. We see that we were only given the information 1.0 nanometers as our only value. So what this is telling you is we're going to put this in two significant figures because 1.0 is just two sig figs. So our final answer is going to be in two sig figs. So therefore, e sub 6 minus e sub 5 is going to give you 6.6 times 10 raised to the power of negative 19 joules. So this is final answer to the first part of the question, which is for us to determine the value in joules. So yeah, that's it. That's basically it. So our first part of the question is done. The second part of the question asks us to determine our final answer in kilojoule per mole, right? In kilojoule per mole. So you have the second part question, kilojoule per mole. Now, before we go on to solve, we can see from the question that we're not given the number of moles of electron, sorry, number of moles of energy. So we cannot really do energy divided by number of moles. But we are scientists and we know this important information. We know that 1 mole, okay, of substance, atom, ion, molecule, element, or any other particle or chemical quantity. Let me just say, not, let me not say other particle, any other or chemical quantity, just basically any other particle, let me just say, or any other particle is always going to give you the Avogadro's number, which is 6.022 times 10 raised to the power of 23 per mole. So basically, 1 mole of anything is always going to give you 6.022 times 10 raised to the power of 23 in terms of its quantity. So I just wanted you guys to know this information. This is from general chemistry. So if you remember your general chemistry, you see that we use this a lot when we're studying general chemistry. So for those of you that may not be chemistry majors, you also did this before you were able to qualify to take physical chemistry. So this is very, very important because it relieves you of having a situation where you are not given the number of moles, right? We're not in a situation where we're given the number of moles. Like, for example, if they tell you to find the molar volume, you just say volume divided by the number of moles given. If they ask you to find molar heat capacity, you'll be dividing the heat capacity divided by the number of moles given. You were not given the number of moles, but you understand the concept that 1 mole of a substance, whatever it is, atom, ion, molecule, element, or usually any other chemical particle or quantity, is going to give you 6.022 times 10 raised to the power of 23 of that basically quantity or whatever. Anyway, so that's what we're going to use. So to do that, we're going to end up having our E sub mole, which is supposed to be in kilojoule per mole. The units for E sub mole, which is energy per mole, is in kilojoule per mole, is going to give you the E sub 6, okay, minus E sub 5, okay, or yeah, that's it. The energy separation that we have in the unit of joules times Avogadro's number. Don't forget Avogadro's unit is just simply 1 over mole or mole raised to the power of -1. So this is just basically what this is. So because we know that, Avogadro's number times the E sub 6 minus E sub 5, we can now proceed we can now proceed to continue the work. So E sub mole is equal to E sub 6 minus E sub 5 is just simply 6.62728 times 10 raised to the power of -19 joules, okay, multiplied by the Avogadro's constant, 6.022 times 10 raised to the power of 23 per mole. So that's basically it. That's basically the answer. So yeah, that's basically it. So we're just going to do it. You can see now that we're going to have joule per mole as the units for this question. So let's proceed. 6.627 times 10 raised to the power of 6.62728 times 10 raised to the power of -19 joules times 6.022 times 10 raised to the power of 23 per mole is going to give you, when you input the information in calculator, you end up getting 3,399,000, okay, and 94.81 joule per mole. So this is going to be our answer. But our work is still not done, right? Actually, before I go on to explain, I want to quickly mention the reason why I'm using the raw value 6.626728 times 10 raised to the power of -19 joules is because whenever you're dealing with calculation in science, you have to use the raw values. Please and please and please do not use what is in the raw values. If you go ahead and use the approximated value like 6.6 times 10 raised to the power of -19, it's not going to give you the correct final answer. So when you're using an answer to solve for further questions or to solve further questions to get another answer, always use the raw values, not the approximated value, so that we have precision in the final answer that we're solving for. So anyways, that's the reason why I use the raw values. If you've been watching a lot of my videos, you're going to see that I've explained this a lot in previous videos, and I'll still try my best to keep explaining it. So we see our answer is in joule per mole. But let's not forget that we're told to do our work in kilojoule per mole. And to do our work in kilojoule per mole, we have to divide by 1,000. So divide by 1000 to get kilojoule per mole. So when we do that, E sub mole will end up giving you 399.09481 kilojoule per mole. Now you're going to be wondering, oof, thank God our work is done. Our work is still not done, love. We still have to remember that we're scientists and we have to put our work in the proper number of sig figs. So when we go back to the question, we see the proper number of significant figures is two significant figures. So we're going to approximate this here to two sig figs. So E sub mole can be rewritten as E sub mole is simply 4.0. Okay, so we're going to put in two sig figs. So in here, times 10 raised to the power of 2 kilojoule per mole. And this is basically the answer to this question. I approximated it to two significant figures and I put the scientific notation so that we can get our answer crisp. So yeah, this is basically the answer of this question in kilojoule per mole. So lastly, we're asked to solve this question in electron volts, which is the third part of the question. So what is the value of energy separation between n is equal to 6 and n is equal to 5 in electron volts? The first thing you have to note is that since we've gotten our answer in joules, we can also use that to solve the electron volts by noting the relationship between electron volts and volts. Now, the relationship, okay, between electron volts and joules, not volts, sorry, electron volts and joules with a J is 1 electron volts is equal to 1.602 times 10 to the power of negative 19 joules. So that is what this is. So now we know that this is the standard information, just like you know that 100 centimeter is going to give you a meter, or 1,000 decimeter is going to give you a meter. So that's what this is. Now, let's not also forget that we solve for our answer in joules, which is 6.62728 times 10 to the power of negative 19 joules. So E sub 6 minus E sub 5 is just simply 6.62728 times 10 raised to the power of negative 19 joules. So that is basically what this raw value is. So we can now use this knowledge to properly solve the question. So we know that 1 electron volts, okay, is going to give you 1.602 times 10 raised to the power of negative 19 joules. Then what is 6.62728 times 10 raised to the power of negative 19 joules going to give you? What is this going to give you? I'm going to denote this here as x, our general unknown. Okay, then of course we cross multiply and we end up with x is equal to 1 electron volt times 6.62728 times 10 raised to the power of negative 19 joules divided by the 1.602 times 10 raised to the power of negative 19 joules. We cancel out the joules. We cancel out the joules. We definitely actually need our final answer in EV. So this is what we need our final answer in. So of course, and like units will cancel out. So 6.62728 times 10 to the power of negative 19 divided by 1.602 times 10 to the power of negative 19 will end up giving you 4.13688 electron volts. So yeah, that's basically the answer. But our work is still not done because we're scientists and we have to put our work in the proper number of significant figures. And when we go back to our beginning of our question, we see that that is the proper number of significant figures is simply two sig figs. You see 1.0 nanometers, two sig figs. So because in two sig figs, our final answer is going to be in two sig figs. So basically E, okay, the energy in terms of electron volts, let me just call it E sub EV, sorry, E sub EV is equal to 4.1, again, two sig figs, mistake, 4.1 electron volts. And this is the answer to this question. So when we go back up, we'll see that we have actually solved everything we're asked to solve. Asked to solve for joules, kilojoules, and electron volts, and we have successfully done all three in this video. So yeah, joules, kilojoule per mole, and electron volts all done. So I'm going to do other problems like this on this channel. There's actually a total of 4 problems like this. This is just one of the 4. So make sure you watch the other ones to be able to grasp the concept. Now, this question that is from the Atkins Physical Chemistry 11th edition is actually not done. There's the fourth part of the question that says to find the value for energy separation in centimeter raised to the power of -1 or reciprocal centimeter. And the method of solving that is quite different from this one's. So I'm going to do those in another video. I'm going to do for all 4 problems in other videos or in one major video. I'm not sure yet. And you guys should watch that in case you wanted to solve all of the questions from all of the sub questions from this particular question in the Atkins. So I just wanted you guys to know that I solved 3 of the 4 purposely because that other one requires a different method. So yeah, that's basically it. If you have any questions, suggestions, or concerns, put it in the comment section, please. And if you're a student who is struggling in any of your STEM-related courses, whether you're in middle school, high school, or college, I am the tutor for you. I help students succeed in all their STEM-related courses as well as mentor them so that they can succeed in their journey through academia. So if you like to book a tutoring session because you love the way I tutor and the way I break down information, please email me at shabbytutoring@gmail.com. I welcome you to my services. So yeah, I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.